So today class is regarding your unit 1. Recap and recall. Recall or recap session. Yeah, PDF is not shared. Just be with us. Before coming over here, I want to share actually. Okay, no problem. I'll share after the class. Okay. So because today's lecture is not nothing to do with the yesterday's it's not a yesterday's class continuation. Okay. I'm considering the unit 1 recall, something like a recap, and along with problems to be worked out. So problems for practice. Okay. So because most of the people are asking for the problems, so initially we started the discussion with the basic definition of the matrices or matrix. So we understood it is a simple collection of m into n elements. So these many elements are there. These many elements arranged in I call elements arranged in, we call m rows and n columns. M rows and n columns. For your mid examination, the unit 1 and unit 2 are the complete syllabus. Okay. Now today is a Thursday, tomorrow Friday, Saturday is also working day. We'll be following maybe I think it is maybe a Monday timetable. Okay, we have still a couple of days are left to finish the rest of the syllabus of unit 2. Okay. So m rows and n columns. So the way in which we are arranging into m rows and n columns resulting into an called m cross n matrix, which we call it as an order. We call it as an order. So order of the matrix is m cross n, which talks about the m rows and n columns. Suppose if these same m into n elements are arranged in, these are arranged in n rows and m columns. So is it possible? Yes, this is also possible. So where the order here, the order will be n cross m. Because I can say I have 6 elements with me. So this can be arranged in 2 cross 3 or 3 cross 2. So 2 rows, 3 elements, or 3 rows, 2 elements. So there I am talking about there are 3 rows, each row containing 2 elements. There are 2 rows, each containing 3 elements. So this is how we are arranging. The possibilities are existing. Okay. Then after that we have taken the types of matrices. We have taken the types of matrices. So under the types of matrices, we might have discussed the concept of symmetric matrix, which we called as A transpose is equal to A, and is called skew symmetric. We call it as A transpose is equal to minus A. This is only the recap. Okay. And we are defining to make this particular thing. So a concept of transpose is defined. What is a transpose? The transpose of matrix is defined to be whatever the rows are there, they are transformed into the columns. So rows into columns. The rows are changed into columns. Vice versa, columns are also changed into rows, but not both simultaneously. So the elements that are there in the row are changed to be a column. So first row is changed to be the first column. The second row is changed to be the second column. Seven, 8, 9. The third column is changed to be the third column. So it's not like that first row is changed to be the third column, second row changed to be the first column. No such order. Okay. The same order we are maintaining. the same number of rows. It's called m rows, change it into m columns. Preserving the order. I'm not changing this way. So I can write 4, 5, 6, 1, 2, 3, 7, 8, 9. See this? This 1, 2, 3 row is now changing into second column. That is not the case. This is not a transpose. The transpose is this one. Okay? So based upon this one, we identify the symmetric and the skew symmetric. Then after that, we might have taken there are different types of matrices, right? So we might have taken singular and non-singular. The another category is called singular and non-singular. So a matrix is said to be singular if A inverse does not exist. So non-singular means A inverse exists. So to be more precise, the other way I can say the det of A is 0, then we say that A inverse does not exist. We can say that the det of A is non-zero, so we can say that A inverse exists. So the singular and non-singular is termed in terms of the determinant. Now here again, the concept of determinant is to be determined. So determinant of a matrix is nothing but, so if A is a given matrix, I'm saying that is a n cross n matrix because the determinant is always possible for a square matrix only. This is square matrix only. This is possible only for the square matrix. Okay? So that is why we are mentioning it is of n cross n matrix. So now I am saying that this is nothing but it is the sigma of Ai, or I can say Aij, and the cofactor of Aij. So this is how we are expanding the sigma over either I or j. You are fixing it. So either I or j, in the sense you have to expand this by either by I. For example, I am writing this is A11 cofactor of, I can write cofactor of A11 plus A12 into cofactor of A12 plus A13 into cofactor of A13 plus and so on and so forth. I can write A1n cofactor of A1n. What is the meaning of this one? This is expanded by the first row. Or if I am expanding, so this is the way we are getting. So this is expanded by the first row. This is first row. So which expansion is this one? If my expansion is coming with this one, if the expansion is coming with the first column, then this could be of this structure. So what is the way now in which I can write? So I am expanding by the first column. So it is A11 into cofactor of A11 plus A21 into cofactor of A21 plus A31. What is 31? This is called 1-1 position. 2-1, 3-1, 4-1. So this is how their positions are taken. Now when I am going with this one, this is A11, A12, A13, like that it goes. So A31, So this is, I can write this. Sorry. So it is a A13 into cofactor of A13 plus and so on and so forth, AN1 cofactor of AN1. Please remember, this is how we are moving. So again, the sense is that my question is, then what could be the cofactor? So what is a cofactor? So the cofactor, so this we are defining, the cofactor is defined for the ith element, jth element. For general element I am saying. Suppose first element A11. So this is nothing but it is the minor of order n minus 1 cross, I repeat, it is the minor of n minus 1 cross n minus 1. By excluding the ith row and jth column. So this is the position of called Aij position. So I'm saying that these two positions are excluded. I'm saying that these two rows and column are excluded. Means they are deleted. That ith row and jth column are deleted from the given matrix. Then the given is n by n matrix. The resulting one will be a n minus 1 cross n minus 1. So whose determinant is multiplied with, I repeat, this is multiplied with minus 1 to the power of I plus j. So that is called the cofactor of Aij is nothing but it is minus 1 to the power of I plus j into the Mij. So what is this Mij? Mij stands for, it is the minor of Aij. So the Mij is multiplied into minus 1 to the power of I plus j is the cofactor of Aij. Then what is the minor of Aij? Minor of Aij is the determinant of the leftover n minus 1 cross n minus 1 by delete ith row, delete jth row, delete jth column. So this is how we evaluated the cofactor. Sir, with determinant we will use alternative. This alternative will come with a minus 1 to the power of I plus j. That's why please remember I am taking all pluses. I took all plus. Because the cofactor is there now. This cofactor will define that minus sign. The definition of cofactor is involving minus 1 to the power of I plus j. So it is a 1 plus 1, 1 plus 2 it becomes minus, 1 plus 3 it becomes plus, minus 1 to the power of 1 plus 3. Minus 1 to the power of 1 plus 4 it becomes minus. So minus plus comes alternatively. Is it clear? Rule number 240? Is it clear to rule number 40? So you need not to bother about that minus plus. It itself will take care of the things. So that is how we are taking the cofactor. Because cofactor is defined in terms of the minor is multiplied with minus 1 to the power of I plus j. That is called the position value. I call it the positional value. It could be either minus or it could be a plus. So this is how the concept of determinant. This determinant is becoming 0. We are called it as a singular. The otherwise we call it non-singular. Is it clear? Now, okay. Now after this, sorry. So if the determinant is 0, it's called singular. If the determinant is not 0, it's called non-singular. If the determinant is becoming 0, then it is called invertible. It is not invertible. It is not, the inverse doesn't exist. If the determinant is non-zero, then the inverse is existing, because the A inverse formula, I repeat, because the A inverse formula we can get it as A inverse is equal to 1 by delta A into the adjoint of A, ADJ of A. So what is the ADJ? It is called adjoint. It is called adjoint of A. So the meaning of adjoint is nothing but it is the transpose of, so I can write this is 1 by delta A into, this is the transpose of cofactor matrix. Cofactor matrix. What is a cofactor matrix? So every element is replaced with, that's called cofactor matrix is nothing but, I repeat, so here A11 is there. So A11 is replaced with its cofactor. So cofactor of A11. So like that, here A1n. So A1n is also replaced with cofactor of A1n. So like that, the corresponding positions are replaced with the cofactors. Sorry, the corresponding elements are replaced with the cofactors. Then I can get a big matrix, the same order. I can get the same order, n cross n matrix. So I can get all the elements are filled. So here A1n is there. I can get cofactor of A1n. Is it 1n? No. This is an1, nth row. So this will be cofactor of an1. an1. Okay, this is clear. So like that, the last will be ann. So it is a cofactor of ann. So again, what is the meaning of cofactor? Cofactor is nothing but, already we have taken, that is minus 1 to the power of I plus j. So the cofactor of aij I am talking about, into the minor of, that is n minus 1 cross n minus 1. So excluding the ith row delete the ith row, jth column is deleted. So delete the ith row and jth row. That is called the cofactor. So all the elements are replaced with its respective cofactors is the cofactor matrix. Take its transpose and divide it with the determinant. That is how the determinant is placing very important role in the evaluation of the universe. So this might have studied at your intermediate. So this is how the comes. And already along with this, we are already aware that if A is a given matrix and B is a given matrix, if A and B are two given matrices, then A plus B is possible only if, I repeat, this is possible only if A and B are of same order. Otherwise, it's not possible. I cannot add a 2 by 2 matrix to a 3 by 3 matrix. Sir, shall we do a small 3 by 3 on this cofactor? It's up to you. It's a choice. Okay, just you can practice it. Anyway, this method we are not going to ask in the examination. Okay. So if they are of same order, then A plus B is possible. Not only that one, A minus B is possible. But when I'm talking about A into B, so when I'm talking A into B, this is possible, the multiplication is possible only if, so it is the number of columns in A should be equal to the number of rows in B. So this is the condition for the matrix multiplication. If it is not there, then we cannot say that the A and B are multiple. I can say that they are not conformable for matrix multiplication. So if this condition is there, so that's what we were mentioning, that if this is a M cross N matrix, this is a K cross S matrix, then if N equal to K, then the matrix multiplication is possible. Otherwise, it is not possible. So that is why, because when I am multiplying the matrix, first row is multiplied the first column. So how the multiplication is taken? So it is by element by element. So how many elements is there in the row? Equal to the number of columns. So my question is, how many elements are there in a row? For this question, what is your answer? This is equal to the number of, how many elements are there in the row? That is equal to the number of columns in a matrix. So that should be equal. So that is why we are mentioning that the number of columns in the first matrix should be equal to the number of rows in the second matrix. Sir, how to calculate det A? So det A, already we mentioned, determinant of A is taken by this one. So determinant is expanded by the sigma of this one and denoted by the det A, which is of n cross n matrix. So for example, I am writing 1, 2, 3, 4, 5, 6, 7, 8, 9 for 3 by 3 determinant. So it is expanded by 1 into the element into cofactor of this one. Cofactor is minus 1 to the power of 1 plus 1, because the position into, excluding the first row and first column, that is 5, 6, 8, 9. I am not simplifying, I am giving the expression. Plus 2 into, excluding the first row and second column, but its position is minus 1 to the power of 1 plus 2 into the determinant of first row, second column is excluded, it becomes 4, 6, 7, 9 plus 3 into minus 1 to the power of 1 plus 3. It is a 1, 3 position into first row, third column are excluded. So it becomes 4, 5, 8, 9. Sorry, 4, 5, 7, 8. So this is how we are making now. See that this plus minus alternatively will take care by this minus 1 to the power of I plus j. Okay, so this is how. Let me not simplify. Now here this is the determinant of a 2 by 2 matrix A, B, C, D is always, it is a AD minus BC. So this is how I can evaluate this, the rest of the things. Yes? So, just wait a minute. So if A is any given matrix, then A plus A transpose whole transpose will be A transpose plus A transpose whole transpose, which can be written as A transpose plus A, because transpose of transpose is A. Now, for any two matrices, A plus B is always equal to B plus A. That is called, it is commutative. It is commutative with respect to plus. Yeah, when I am talking about this one, this is expanded by the first row. Please remember, this is expanded by the first row. Suppose I can also expand it by the second column. This is also possible. So what do you do now? 2 into, what is the position? Minus 1 to the power of 1 to position. 1 plus 2 into the rest of the case 4, 6, 7, 9. Plus 5 into minus 1 to the power of, what is the position? 2 plus 2. Into excluding the first, second row, second column, 1, 3, 7, 9. 1, 3, 7, 9. Into 8 into minus 1 to the power of, what is the position? 3 to position. Minus 1 to the power of 3 plus 2. Into excluding this one, 1, 3, 4, 6. So that is how we can write it. This is clear? So that is why it is expanded by any row or any column. You can choose any I or any J. But fix it, either expanded by a row or expanded by a column. So if you want, I can write over there. So if I am expanding this by, so I am expanding this. So here I can write. Okay. So that is 2 into, so 2 in the sense 2 into minus 1 to the power of position is 1 plus 2. First row, second column into the determinant. What is the determinant? Determinant of excluding the first row and second column 4, 6, 7, 9. 4, 6, 7, 9. Plus 5 into minus 1 to the power of, its position is 2 to position. So minus 1 to the power of 2 plus 2 into the determinant excluding the second row, second column 1, 3, 7, 9. 1, 3, 7, 9. Check it. Previously 2 in the sense first row is eliminated, second column is eliminated. Okay, so 7, 9. Plus 8 into, what is the position of 8? 8 position is third row, second column. So 3 plus 2. 3 plus 2 into, so excluding the third row and second column. Third row and second column 1, 3, 4, 6. 1, 3, 4, 6. You please remember this value and this value will be the same. Why must we keep minus 1 all the time? Yeah, this is because of the reason, this minus 1 because of the reason it comes with a positional value. I call it as a positional value. Positional factor, I call it as a factor. Okay, this is how they developed. The basic definition of the determinant is defined as this way. See this, few concepts will be defined likewise. So determinant has some applications over there. So they define like this, okay. So I call it a positional factor. Yes, instead of taking minus 1 to the power of so and so forth, you may take alternatively. But see that alternatively means the question comes, should I start with the plus or should I start with the minus? Yes or no? Because when I am evaluating this, here the first one, for the first one, it is coming with the minus 1 to the power of, so it is starting with the plus. But if I am extending by the second column, initially it starts with minus. Please remember, if plus minus are going to change, your value there is maybe, suppose there it is a minus 12, there, if also here you are starting with the plus sign, it will be minus 12. This is clear. So that is called, irrespective of the column or row you are selecting, to expand the minor, that's called determinant, the value will be same. Okay. So that is why the positional factor is taken care. It's not all the time you are starting with the plus sign. That depends upon the position or the row or the column. That's clear? Sorry. So with respect to plus, it is always commutative. But when I'm talking about A into B, that's called multiplication, I cannot say that B into A. This is not true for all the time. Not true for all the time, or for all matrices A and B. For all matrices A and B. This is not true. Means for some matrices it is true. So for those matrices it is true, I call them, it is commutative with respect to the multiplication. So we cannot assure that this is there for all the matrices. So this is not commutative. It is called not commutative. But as per the matrices is considered A plus B is equal to B plus C, this is always A plus B plus C. This is always true. It is called associative. The beauty of this matrix multiplication, it follows the matrix multiplication is associative. So A into B into C. So this is always true. So this is both associative with respect to plus as well as the multiplication. Multiplication is denoted by dot. Okay. So using that particular sense, now this could be written. So what is the meaning now? This is my B power B transpose is equal to, I got B. Now what is the meaning that for any matrix capital A plus A transpose is always symmetric. Do you agree? Is always symmetric. So irrespective of the nature, whether it is symmetric matrix or not, but A plus A transpose is always symmetric. That is one beautiful result. And similarly, for any matrix A, you are talking about A minus A transpose. Now let us talk about its whole transpose. It becomes A transpose minus A transpose whole transpose, which could be A transpose minus A, which can be written as minus A transpose. Do you agree? I have taken minus common. So now I got B transpose is equal to, it is minus B. So what is B now? So for any matrix A, irrespective of its nature in terms of symmetric or skew symmetric, now for any A minus A transpose is a skew symmetric. All the time. So for any general, and again please remember, when I am taking suppose A is taken to be 2 cross 3 matrix. Now what happens to A transpose? It could be 3 cross 2 matrix. Now is it possible for addition? No, because I mentioned addition is possible if they are having same order. So the addition is not possible. So that is why we are taking A is not a general M cross N matrix, but A is a general N cross N matrix. So A is any square matrix is added. Is for any square matrix A. We have these two observations. This is clear? Okay. So up to this is clear? Now making use of these two observations, I can make for any matrix A can be written as 1 by 2 of A plus A transpose plus 1 by 2 of A minus A transpose. Do you agree? See this? What happens to this sum? 1 by 2 A plus A transpose plus 1 by 2 A minus A transpose. When this is symmetric, when I multiply with 1 by 2 is also symmetric. So this is a symmetric matrix. This is a symmetric. This is a skew symmetric. Skew symmetric. So always I can make any square matrix can be represented as sum of any square matrix capital A can be expressed as a sum of what? Sum of symmetric and skew symmetric matrix. Sum of symmetric and skew symmetric. So actually this is a theorem, but okay, let me not do that. So this is what we call. So is it clear? Any square matrix, any square matrix can be expressed as a sum of symmetric and skew symmetric matrices. This is clear? Next write down. Now, the concept of orthogonal matrix. So this is a very important property we'll be using in the case of the later on part called diagonalization of a given matrix. So orthogonal matrix. So what is the meaning of this? If A is said to be orthogonal, which is of order n cross n, because if it is not a general matrix, because I need to go with the transpose. So if A into A transpose is I, we call, which is equal to A transpose into A. Please remember both should be the case. Then we call A is orthogonal. Then such A is called orthogonal. So what beautiful property of this orthogonal is, I have A, so which is of n cross n matrix, the another A, so taken to be transpose, which is also of order n cross n. Because if A is taken to be of m cross n matrix, then A transpose would be n cross n matrix. Now what could be the A into A transpose? So this is of n cross n matrix and this is of n cross n matrix. Then this matrix multiplication is possible. Then the result will be a new matrix B, which could be of m cross n matrix. For example, I am taking its reverse, A transpose into A. Now it becomes, what is A transpose? A transpose will be n cross m and A will be of m cross n matrix. Then these two are same. Then the result will be another matrix called C, which will be of n cross n matrix. Please remember, the order will play a very important role. That's why I am fixing the order n cross n. Then this will be of n cross n. So this is my A and this is my A transpose. So the multiplication says this first row is changed to be the first column. This is my R1 change it to C1. My R2 is going to change it to my C2. Do you agree? Because the transpose will take care of the changing the rows into columns. Then the result, I am saying that the result should be an identity matrix 1 0 0 0 0 1 0 0 and 0 0 1 so on so forth 0 so on so forth 0 0 0 so on so forth 1. So what is the meaning of this one? Where I am multiplying the row 1 into column 1, that's called R1 into C1. But what is your C1? C1 is the transpose of R1. Do you agree? C1 is the transpose of R1. So a row is multiplied with a column. A row is multiplied with the column. Similarly, when I'm talking about A transpose into A, so this is my A transpose and this is my A. So the transpose is nothing but now, actually they are columns. So here I can say this column is changed to be the row now. Whatever it is, both the row is changed to column. Now here you are talking about the row into column. So what is actually, this is nothing but the C1 which is happening in my A is transformed into the row because of transpose. Now here the multiplication is R1 into C1 can also be written as C1 transpose C1. Do you agree? Whatever the column is there in my A is changed into row. But here whatever the row is there is changed into column. Both are same. So that is why we are mentioning that if you are multiplying a vector with the vector, you are getting is 1. And a row is multiplied with any one of the other rows or other rows transpose. That's called, I write it as Ri into Ri Rj that's called transpose. When I'm talking about this one, which will be 0 if I is not equal to j, and this is equal to 1 if I is equal to j. Not only this one, with respect to C also I can take up, this is a C1 transpose Cj. So this is 0 if I is not equal to j, and this is equal to 1 if I is equal to j. So this is the very important property we are calling for the orthogonal matrix, where this property is called orthogonal property, and this property we call it as orthonormal property. I call this a normal. Orthogonal. This is called orthonormal. So this is how it makes. Sir, orthogonal matrix is one of type of square matrices? Yes. Orthogonal matrix, when you are talking about, it should be a square matrix. A square matrix is said to be orthogonal if you have these two. Please remember, not only one condition. I should have these two conditions. There is two conditions. What are those two conditions? One condition is this one. One condition is this one. The other condition is this one. So that is why we should have two conditions. If I am having only this one, the reverse is not true, then this is not an orthogonal matrix. That is why we are mentioning this and this. A row is multiplied with the transposed, or a column is multiplied with the transposed. You must get this property, so that it satisfies the orthogonal as well as the orthonormal. This is clear? So because in the latter part we will be talking about eigenvalues and eigenvectors. So eigenvectors of a real symmetric matrix will be behaving like this. Okay? Non-singular and invertible. Yes, invertible matrices are the things whose inverse is existing. Non-singular matrix is the one for which determinant is not 0. For determinant is not 0, we call it as a non-singular. And if A inverse exists, it is called invertible. Okay, this is called invertible. This is called non-singular. But there is a connection between these two. A non-singular matrix will have an inverse. Invertible matrix, for an invertible matrix, the determinant is non-zero. This is clear? So this is vice versa connected. So next, so one problem is that, so I don't work out the problems, just for the sake of your practice I am giving the problem. So it's a for practice problem. Express capital A is equal to 3 minus 2 6, 2 7 minus 1 5 4 0 as a sum of symmetric and skew symmetric matrix. So what to do now? You need to evaluate A plus A transpose, it's half, and A minus A transpose, and it's half. Then you add up. That is the case. My next problem. So if you need any problem for practice for A inverse by adjoint method, you can make this one. Find A inverse by adjoint method. That means you need to use A inverse is equal to 1 by dta into adjoint of A. So use this formula where the A is given by, please remember that determinant should not be 0. So it is 113, 1 minus 3, 1 plus 3 minus 3, and minus 2, minus 4, minus 4. Okay, next. The P3, show that the matrix A is alright 1 by 3, 2 by 3, and 2 by 3. And 2 by 3, 1 by 3, 2 by 3, 1 by 3, minus 2 by 3, 2 by 3, minus 2 by 3, and 1 by 3 is orthogonal matrix. So you need to prove that A into A transpose is equal to I, and A transpose into A is equal to I. You need to prove both. Okay. Then after that, so these are the three problems. Let me remember P3 is my last problem over there. Then we started with the concept of elementary transmissions. Elementary transmissions. Okay. Right. So what are the elementary transmissions? There are two types of elementary transmissions. There are three elementary transmissions related to row. There are three elementary operations related to column. So we call them as row operations. We call them as column operations. So totally 6 basic operations. Okay, so there are only 6 elementary operations. We call them as transforms. So the first operation related to row. So the similar thing is possible with the column. But the same thing is with respect to the column. So that is first row is called, I denoted by Ri is interchanging with Rj. Ri is interchanging with Rj. The simple way of writing is Rij. So saying that ith row and jth row are interchanging. So previous slide. Okay. Previous slide. Yeah, just wait a minute. Okay, now this is related to the row operations. With this is called interchanging of any two rows, or say interchanging of ith and jth rows. Okay, this is my first operation. The second operation is Ri is changing as k times of Ri. Precisely k is non-zero. Is it audible? I think so. Let me confirm. Okay. So this is called the kth multiple. So saying in the simpler way, I can write KRI. So that is called multiplying. I can say multiplying the ith row with a non-zero scalar. I call it as a scalar. Non-zero constant, saying simply. Now similarly, I can write the last way, that Rj is changing as Rj plus k times of Ri. So it is, I can say this can be imagined as the combination of these two. Check it. A kth multiple is always possible. After multiplying the kth constant, it is added to some jth row. So that is called, simply saying, I can write Rj plus k times of Ri. So please remember all the time, the first one you are writing is the changing variable, the changing row. Okay. So that is called the kth multiple of ith row is added to jth row. So this is how we are mentioning. Now similarly, I can also copy the Cij, the k times of Ci, and Cj plus k times of Ci. So the similar sort of explanation will carry forward with the small change that the row is replaced with the column. So these are the six basic row as well as column operations. Okay, and these are used to evaluate, because when a matrix is considered, I'm mentioning that when matrix is considered, A is considered. So on the matrix A, I apply the first operation, or I apply this operation, or I apply this operation, or I apply this. Any one of these six operations, any one, I can say any one of six operations, any one of these six operations you apply. So I'm saying that OP1 is applied, operation 1 is applied. So what is that OP1? We don't know. Any one of the six operations. Then this is resulting into a new matrix. Please remember, I'm saying that 1, 2, 3, 4. I have applied R2 and R1 are interchanged. So it becomes 3, 4, 1, 2. Now please remember, can you say that these two are same? No, they are not same. But I can say this is similar to 3, 4, 1, 2 by applying the operation R1 interchanged with R2. Please remember, these elementary transformations, on applying of these elementary operations, we will be getting a new matrix. We call that